Welcome to the last lecture of week 10. Up until now we have seen inclusion exclusion based algorithms. We have also seen an algorithms based on matrix multiplication. But today we are going to talk about polynomial methods. So to do that, let me introduce some of the basic concepts that we will be encountering in this lecture. Okay, and this is as before, the slides are by Lucas Kowalik from an old school, but that will serve our purpose. So the concept we need is the concept of a field. This is not a course in maths or this, but I still let me tell you what fields are. Basically it's a triple. So basically field is basically set which are bestowed with a couple of operations, some addition, some multiplication. That is what it generally called, but they are basically some binary operators and they satisfy some property like some associative property, commutative property, distributive property, and there exists a notion of additive identity which basically tells that then there is a multiplicative identity, basically that if you multiply with that then you will get the same element, and similarly additive identity is like 0, which if you just add it with you get the same element. So there are some small number of properties that this set needs to satisfy, and there is also a notion of multiplicative inverse, which basically means that for all a in f minus g there exists b in f such that a dot b equal to 1. So for example, if you take rational numbers, real numbers or complex numbers, then they form a field. But if you look at integers, then they do not form a field, because if I give you a number 2, there is no number in integers that if I b, so that if you multiply with that it gives you 1. So while integers are not a field, but rational numbers are field, because given any number 2 I can give you 1 by 2. If you give me 1 by 2, then I can give you 2, so on and so forth as a multiplicative inverse. So this is a very good exercise to check that fields such as rationals, reals or complex satisfy this property. Okay. So yeah. So you could look at this concept up from also from from Wikipedia or from web. But these are infinite field, meaning their sizes are like Q, R and C are of infinite size. But the kind of field we will be working with will have size 2 to the power L, and the only things that we need to know about this field is the following. They exist for every L in natural number. So there exists a field of size 2 to the power L for every L in natural number. So that's the first thing that we need to know, and we can perform arithmetic operation very fast in this field. So arithmetic operation only depends logarithmic in the size of the field. So that's the second thing. And thirdly, which is most important, is that they are of characteristic 2. That is 1 plus 1 in this field is equal to 0, which implies that if you take any element and you add with itself, then this is 0. Okay. So a field is called characteristic R if you then you have to add a r times to get it 0. But the kind of field we will be talking about, field of characteristic 2. So basically, in particular, just like if you take any element, add it twice, then it is going to be 0. Okay. So basically, in this field, if anything occurs even number of times, then they will evaluate to 0. So this is the three things important to know, that we will be only talking about field of size 2 power L. They exist for every L in natural number. We can perform arithmetic operation very fast in this field. In particular, like in logarithmic, the size of the field, they are of characteristic 2, that is 1 plus 1 is equal to 0. And in particular, for any element A, we have that A plus A, or in other words, for every number A, minus A is its additive inverse. Okay. Or A is equal to minus A rather. Okay. So its additive inverse is itself. Okay. So these are the few things that you need to know. They exist. So a finite field of size 2 power L exists. They exist for every L in natural number. We can perform fast, and if I take any element and add to itself, then that will cancel out, or that will become 0. Okay. So this is all that we need to know about finite field of characteristic 2. Okay. So, another concept that I need is of multivariate polynomial. So, you fix a field f, then monomial is an expression of the form ax1 to the power c1, x2 to the power c2, xn to the power cn, where a belongs to the field, x1 to xn are variables, and c1 to cn are natural number union 0. So, yeah, then what is the degree of a monomial? You just sum the coefficient, sum the powers of these xi. This a is called coefficient. Okay. So, degree of m is basically summation of the power. So, example, look at 5 x 2 to the power 3, x 3 to the power 3. What is its degree? 7 plus 3, 10. And what is the degree here? It is 2114, because every one has 1. So, in this monomial. And what is a polynomial? It is basically a finite sum of monomials. For example, so polynomial is an expression of the form you like. So, you have a different term, and for every term you could have a you could have a coefficient coming from and yeah. So, a coefficient coming from your field. So, where this is non-zero only for a finite number of tuples. So, we are not talking about polynomial with infinite number of monomials. So, those have a very different terms, different name, but in polynomial it is just a finite number of terms in this summation. Okay. And what is the degree of this polynomial? Degree of a polynomial is a maximum degree of its monomial. So, whatever is the maximum of the degree of each of this monomial, that is the degree of a polynomial. So, for example, x1 plus x2, what is its degree? Is 1. x1 to the power 3, x2, what is its degree? So, here the monomial has degree 4, this is 7, 3, 10, this monomial has degree 5 plus 6 plus 1, 7, so maximum is 10. So, this is, so similarly, this is just one term, and 0 has it's a 0 polynomial, it has its degree is 0. Okay. Okay. So, this is why are we interested in multivariate polynomial is because of what is known as Schwartz Zippel Lemma, and this is at heart of a lot of randomized algorithms or even otherwise. So, what does this say? So, let us try to understand. So, you suppose you are given a non-zero polynomial of degree at most d over a finite field f. Okay. So, suppose you have a polynomial p x1, x2, xn. So, this is a n-variate polynomial. So, what is given to us is an n-variate polynomial. Okay. So, what is given to us is an n-variate polynomial. Okay. What is its degree? Degree is d. Okay. And degree d over a field f. Okay. Now, what you do? You fix some s subset of f. This is finite. Okay. Now, from this you sample n values. Okay. So, now what we are going to do? We are going to sample a1, a2, an uniformly at random from S. So, that is ei is chosen with probability 1 over S. This is what it means. Okay. Then what does it tells us? Okay. Then it tells us that now what you do is that now you evaluate. Now, what are we going to say? We say now let us evaluate the polynomial p at a1, a2 dot 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 an. So, now let us look at p a1, a2, an. That is, you substitute a1 for x1, you substitute a2 for x2 dot 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 xn an for xn. You evaluate this polynomial. Okay. So, this is what it means. Then what is the probability? So, then it says look, probability that this is equal to 0, and look what are we assuming? It is a non-zero polynomial. Okay. It is important. So, what is the probability that this is equal to 0 is upper bounded by d times mod s. Okay. So, if the polynomial has small degree, right, then what it says to you that look, I have a polynomial, okay, it might be very big polynomial or something, right. But suppose I can evaluate at a random selection of point, then the probability that it is that, so look what happens, that it could be that the polynomial already was 0, then of course it will evaluate to 0. But polynomial may not be non-zero identically, but because of our selection of a1 to an, this is like I have evaluated it to 0. Okay. Then the probability that it is evaluates to 0 is at most d times s. Okay. Now, the people who are aware of field theory or something should realize that suppose p was just a polynomial of degree d, and like it is a univariate polynomial. Then this has how many roots? Think for a minute, pause. So, it has at most d roots, right. So, what is the meaning of roots? Basically, b is called root of px if p of b equal to 0, right. So, we know that it has at most d roots, then definitely if I pick a set S, then at most d points from here, if I pick that, on that evaluation p of this will be 0. So, if S is very large compared to d, then chances of hitting these roots are very low. So, definitely those people who know this theorem will know that for univariate polynomial this is obvious. So, what is a good thing about this proof is that it generalizes the property of univariate polynomial to a multivariate polynomial. Okay. So, for d equal to, so for univariate polynomial, the proof follows from this what is called fundamental theorem of algebra. Okay. So, that or from the fact that univariate polynomial of degree d has at most d roots, right. So, if I take a set S which is very large and randomly pick a point, then chances of hitting the roots are at most d over mod s, right. And this is generalization to not a univariate polynomial, but a multivariate polynomial. Okay. So, what is Schwartz Zippel Lemma says is very simple. Let p be n variable polynomial of degree at most d over a finite field, and then if we pick an S, if we pick a finite subset of f and then sample a1 to an the values for x1 to xn uniformly at random and evaluate the polynomial at these points, then probability that we started with a non-zero polynomial and we get a 0 polynomial is proportional to d divided by s, where d is the degree. Okay. Okay. So, this is something. So, what is a typical application of this? We can efficiently evaluate a polynomial p of degree d, okay, and we want to test whether p is a non-zero polynomial or not. Then we pick S, so that the cardinality of S is at least 2d, and we evaluate p on a random vector x in Sn. We answer S if and only if we got px is not equal to 0. So, if p is the 0 polynomial, we will always get no, otherwise we get yes with probability at least half, and you can boost this probability, right. You can boost this probability, okay, to anything. Like for example, if I would have picked up S not 2d, say 10d, then this will be how much? D over 10. So, this will be 1 minus d over S, right. So, it is at least will be 9 over 10, right, if you choose 10d. Okay. Yeah, 1 over 10, so 9 over 10d. Okay. And this is called Monte Carlo algorithm with one-sided error. Why it is one-sided error? Because look, at one side if it is a 0 polynomial, you will always answer 0 polynomial. It is only when you are given a non-zero polynomial that you might say it is a 0 polynomial, but that happens with very low probability. So, this is a typical application. So, for example, so what is the take home message? We can test whether polynomial p is a non-zero by a single evaluation of p in a random vector. Okay. So, this is a take home message that you should take about Schwartz Zippel Lemma. Okay. So, suppose very simple. So, two multivariate polynomials p q given as an arithmetic circuit, and you want to does p is equivalent to q. Why? Because a polynomial described by arithmetic circuit of size s can have exponentially many. So, you could have a small circuit. Okay, so if you do not know about these things, that is perfectly fine. But look, if you look at a big monomial, like big polynomial, you might have a very succinct representation of the circuit, and you can also evaluate this succinctly. Then maybe writing down all the terms and then evaluating could take you lots and lots of time, and checking whether given two polynomials p and q, writing them down explicitly could be very huge. So, you do not want to like write them explicitly, right? But how can you check whether two multivariate polynomials p and q given an arithmetic circuit or a very succinct representation, like very polynomial, very small, how can you check whether they are equal? That is very easy. So, you test whether polynomial p minus q is non-zero or not using the Schwartz Zippel lemma. If p is equal to q, then p minus q is a zero polynomial. But if they are not equal, p minus q is a non-zero polynomial. Okay. So, now what you do, look at p minus q, you compute its circuit p minus q, and then you based on this degree, you pick up a sum set S, you do a random evaluation, and you can say, so basically it allows you to test whether two polynomials are equal or not, at least in this example, in a very simple, in a polynomial time. Okay. Okay. So, that is all. So, but that is all that we will talk about Schwartz Zippel lemma, and now we will move to an algorithmic application of this. So, the tool is the following, that if you are given an n degree invariant polynomial of degree at most t over a finite field, and you pick up a big finite subset f of S, and if you sample values from this uniformly at random, then the probability that if you evaluate the polynomial at these points, it will evaluate to 0, given though you have started with non-zero polynomial, is proportional to, is at most degree divided by the set size. Okay. Okay. So, given this, so we will talk about an algorithmic application of this. Okay. So, the problem that we will study for an application is we will apply this machinery or the Schwartz Zippel lemma based algorithm to design a much faster algorithm for k path, but we will be talking about directed graph G, and later we will see how we can do this problem on undirected graph. But for now, we will be explicitly talking about directed graph. So, what is an input? You are given a directed graph G and integer k, your parameter is of course k. Okay. And your question is, does there exist a directed path on k vertices in G, right? So, up until now you have seen an algorithm with running time 2e to the power k n to the power big O of 1 via color coding for this. Okay. So, in this lecture, we will try to outline an algorithm with running time, but a randomized algorithm, of course, and of course, we will apply Schwartz Zippel lemma. Okay. 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 So, that is a goal. So, the goal is to study a directed k path problem in a directed graph and design a randomized algorithm and design a randomized algorithm for this with a much more efficient running time, and to do this we will use Schwartz Zippel lemma. So, let us just get started. So, what is the first goal will be? So, now that we would like to apply Schwartz Zippel lemma, so first of all we have to cast our problem, or we have to find a polynomial p over a field f, and we want to say, look, this polynomial does not evaluate to 0 if and only if g comma k is a yes instance, right? Because to apply Schwartz Zippel lemma, okay, so what are the ingredients to apply a Schwartz Zippel lemma? We need polynomial of small degree, whatever that means, okay, and relation of polynomial evaluation polynomial to our problem. Okay. So, that is okay, and And then because if there is some relation to a polynomial of small degree, then we will do an evaluation of this polynomial, and based on the evaluation's answer, we will say something. Okay. Okay. So what I want to say that we want to find a polynomial P. We'll say, look, P is not equal to 0 if and only if G comma K is S instance. So in our case, what it will be that I will make a polynomial such that this polynomial is not equal to 0 if and only if G comma K, G has a directed path on K vertices. This is it. So I want to find a polynomial P over finite field F, and in fact, let me tell you straight that the finite field F that we will work with, okay, will be of size some 2 power L, and its characteristic will be 2, which means that you take any element a plus a and you add it to itself, it is going to evaluate to 0. Okay. So this is the kind of field we are going to talk about. Okay. So field, the nature of field is fixed. All we need at this point of time is to find a polynomial such that this polynomial is identically non-zero if and only if G does contain a directed path on K vertices. Okay. But of course, there is one important requirement of this polynomial is that we should be able to evaluate this polynomial efficiently, right. So, for example, if I could write this polynomial succinctly as an arithmetic circuit or some way to evaluate this polynomial very, very efficiently. Okay. And this notion of efficiently is what will determine the running time of this algorithm. Okay. So, we need a notion of potential solution. Okay. Why? Because this potential solution will constitute a monomial in the polynomial, right. I say, look, this is a particular, this could be a potential solution, this could be a potential solution, this could be potential solution, and for each potential solution, we will create a monomial and we will say, look, yeah, because somehow we need to, in this polynomial, somehow we need to capture these potential solutions. Okay. So, what is our first, like, so maybe what is a potential solution? Of course, a potential solution is a path on K vertices, right? A potential solution is a path on K vertices. But unfortunately, such a polynomial is hard to compute, because in some sense it is like you are talking about finding an algorithm for finding a directed K path, and directed K path itself is constituting, like, a polynomial itself has a monomial for each only K paths, then that kind of polynomial looks a bit difficult to or hard to compute. Okay. So, this is just a very big overview. So, notice that when we were talking about, say, Hamiltonian path algorithm using inclusion exclusion, we talked about walks on K vertices, because what is a walk on K vertices? Walk on K vertices is K vertices such that vertices could repeat and adjacent, like consecutive vertices, have an edge between them. Okay. But they may not, but if you look at, but in walk, if the vertices are not repeated, then they constitute a K path. So, it was like a kind of slightly we relaxed this idea from path to walk, because walk was easy to compute. Okay. This notion almost works, but we will use some coloring to make computation easier, as we did in color coding. So, we will not only need walks, but we will need some colorful kind of walks, because that will help us to compute these paths, like computation will be efficient, right. Because remember color coding, how did we do? Because it was not easy to compute things properly. So, first when we did coloring, then we were looking for a colorful path, it allowed us to do some sort of dynamic programming. So, all these are encompassed into one straight application, is that is like we encode all this, like coloring idea as well as relaxing idea in a monomial itself, as we will see in a minute. Okay. So what are the potential solution? So, walk on K vertices that are colored. Okay. Colors that we will use will come from 1 to K. This is exactly like color coding, right? That colors were always used from 1 to K to color K vertices distinctly. So, that is where this comes. So, okay. So, colors, so walk on K vertices. So, what are our potential solution? Walk on K vertices that are colored. For look at, for example, V, W, U, V, X. So it's a, look, it's a walk, because, and so this is vertices, and these are like 1, 2, 3, 3, 4 is a color. Okay. So this represents color and this represents path. Okay. And what is a colorful potential solution? A colorful potential solution is the one where even if the vertex occurs second time, okay, you assign a different color. Okay. So since it's a directed K walk, you have a notion of first vertex, second vertex, third vertex, fourth vertex, fifth vertex. Every vertex should be assigned distinct, like every occurrence of a vertex should be assigned different color. Or either on other work, if you look at the K vertex, look at the first vertex of the path, second vertex, they all have distinct colors. The colors do not repeat. So here, look at this. The same, this is not a colorful potential solution, because on U and V we have given U and V, we have given a different, what do you call, same color. Okay. So you should see a distinct from the color coding, right? Color coding, we first assign colors to all the vertices. That is not what we are doing now. Okay. So because once you have assigned a color to a vertex, then same color. But look at V here. It has been colored 1, it has been colored 5. So that idea, one should not confuse with that idea. Okay. So first let's just worry about this. So what is a walk on K vertices that are colored? So you are given a walk, and K colors means just you assign color to this occurrences of vertices. They are colorful if each vertex and each of their occurrences get distinct color. So basically this is what is the colorful potential solutions. Okay. Okay. So although that this is important point, that in colorful potential solution also vertex can repeat, right? Because ultimately we are still talking about walk. It's just that every occurrence of vertex gets different color. Okay. So when you are watching this video, pause for a second and absorb this definition. Okay. So now we are talking about, we will generally most of the time we will talk about colorful potential solution. Okay. Now, so we will denote the colorful potential solution by CPS. So what is an incorrect CPS? Walk is not a path. So for example, look at this, V, W, U, V, X. So V is repeated here, V is repeated here. So although the colors are distinct, okay, since vertex are repeated, it is not a path. So what is the correct CPS? Walk is a path, right? So now we will only talk about colorful walks, and it is an incorrect colorful potential solution if walk is a walk, and it's a correct colorful potential solution if walk is a path. That is, every vertex that occurs on the walk are distinct. So for example, V, W, U, X, Y. Okay. So this is a correct colorful potential solution. This is a incorrect colorful potential solution. Okay. So that is, all vertices are different here, V is repeated here. Okay. So again, so these are the two notions that we will use going forward. Okay. So what is an observation? Original instance is a yes instance if and only if it has a correct colorful potential solution. Okay. Why? Forward direction is very easy, right? You start, suppose you had U, V, W, X, Y, then just give 1, 2, 3, 4, 5. So you like just give distinct colors to it. Okay. And if you have a colorful potential solution, then you know that you are talking about K path. So this is a very simple observation, but it's a useful observation to have. Okay. So if you have a colorful potential solution which is here, just forget these colors, and what you are left with is a K path. Okay. Okay. So what are we going to do now? So our polynomial is going to have, as I told you before, for S called denote all colorful potential solution, okay, including incorrect as well as correct potential solution. Okay. Correct colorful potential solution and correct. So S call denotes the colorful potential solution. Okay. Both correct colorful potential solution as well as incorrect colorful potential solution. And what is my polynomial? Polynomial is very simple. It's a summation over, you go S in S call and a monomial with respect to S. Now notice that S call could have, like, this number of monomials in this polynomial could be of n to the power big of k size. So we are making a polynomial, but we can't explicitly write down completely and evaluate it, right? Whatever that polynomial, we have not talked about it, but just by the look of it, it should point to you that it's a very big polynomial. So we cannot write it down explicitly, but we need to find ways to evaluate P effectively so that we can apply Schwartz Zippel Lemma. Okay. So what do we want? We want correct CPS corresponds to unique monomials in P. So if you have a correct colorful potential solution, they should correspond to a unique monomial in P. And for incorrect colorful potential solution, we would like to partition into pair S comma T, right? So that monomial of S is equal to monomial of T. Why it is important to do that? Well, right. So incorrect CPS, we would like to partition them into 2 elements each, and each part has 2 elements, they correspond to the same monomial. Okay. So if they correspond to same monomials, then what happens in the, like, for these 2 times, you have same monomial into 2, right? So if you evaluate this P over a field F of characteristic 2, then because of the coefficient 2, what is going to happen? Look, x1 to xn, you will fix these numbers, right? So you choose in this number a1 to an. Now they are same monomial, so as a number they will be same, but counted 2 times. So over a field of characteristic 2, all this will evaluate to 0, right? So if we have S in S correct, S in S incorrect, okay, over a field of characteristic 2, once you evaluate over this, because you have paired them up, this will vanish, this will go away, right? So the only thing which will be left is S in S incorrect. So this is why we are using a field of characteristic 2 to nullify the effect of incorrect CPS. And this is the way generally is used, that you look at a larger object where you embed the right object, and you say that, look, everything else when I do over a field of characteristic 2 will cancel out each other. Okay. So how do we evaluate this? That's a question. But first of all, we have not even told you what monomial of S is. So let's remedy that situation and let's define the monomial in potential solution. Okay. So we are going to have a vertex and color variable. So what is a vertex and color variable? So for every vertex V, we are going to have a variable x v comma I, v in vertex set, I in 1 to k. And we are going to have a edge variable y e, e in a of g. Okay, it's a directed graph. Remember. Okay, so a b is not same as b a. Okay, so for every vertex, how many variables we have? K variables we have, right? A vertex name and the color it is assigned. And how many other edge variables we have? Like admin. So total number of variables we have is n k plus m, where m is number of edges or arcs and n is the number of vertices. Okay, and you are given a walk w. We will have 2 functions, a color function and a vertex function, let's call it. What is a color function? Okay, given a walk w, we will have a monomial. Okay, so given a walk w, a coloring function and another function f, we will. So what is color of I represents the color of ith vertex of w. Okay, and what is f of I represents the ith vertex of w, right? So this is a map from 1 to k to 1 to k, but this map is from 1 to k to v of g. So it will tell us what is the 5th vertex. 5th vertex is the vertex v. What is f of 7? Oh, it's 7th vertex. So 7th vertex is y or whatever. And what is the coloring function? Will say, oh, for the first vertex color is 5, for the 4th vertex color is red, or so on and so forth. I'll give you an example in a minute. Okay, so again, spend a minute and look at what is our vertex and color variables, what are our edge variables, and what will our monomial consist of. Monomial will consist of Three things: a walk, a coloring function, and a vertex function. Okay. So here's an example. So look at x, u, v, w. What is my coloring function? And so coloring function is function from 1 to 4 to. So suppose color of 1 is 1, color of 2 is 3, color of 3 is 4, color of 4 is 2. So basically it will mean that, and what is function from 1 to 4? F of 1 is x. What is a second vertex is u, so say f2 of u. What is the third vertex is v, so f3 is v. What is the fourth vertex? So f4 is w. Okay. And what is color? Oh, so this first vertex has been assigned color 1, second vertex has been assigned color 3, right? Third vertex has been assigned color 4, fourth vertex has been assigned color 2. Okay. Now, what is a monomial corresponding to w, a coloring function, and f will be? Okay, fine. So, it is a multiplication of vertex color variables on this. So, I equal to 1, what is this? It tells you what vertex it is and what color it has been assigned. So, for example, what is the first vertex? X, what color it has been assigned? 1. So, x1. And it is a product. So, what is the second vertex? It is a u, and what color it has been assigned? 3. So, u3. Okay. Okay. What is the third vertex? V, right? And what is the color assigned? 4. What is the fourth vertex? W. And what is the color assigned? 2. And the color and what is I equal to 1 to k minus 1 edges from fi, f of I plus 1. That is it. So, yxu, yuv, vw. Okay. So, this is a monomial which corresponds to a walk, coloring function, and a f function, or the vertex representation function. Okay. So, let S call denote the CPS, and this what we wanted: correct CPS corresponds to unique monomial in P. Incorrect CPS we should be able to partition into pairs S comma T such that monomial of S is equal to monomial of T. So, let us try to do that. Okay. Let us show B first. Okay. Monomials corresponding to incorrect CPS will cancel out. Okay. So, let us W be V1 to BEB, a walk, a coloring function, and F, and color of is k to 1 to k, and f of k Vg, f of I it is a Vi. Okay. So, question is, what do we know about W? W is a walk, and hence there exist indexes I and j such that, what is the index I and j such that f of I is f of j, which is Vi. Okay. Okay. So, basically I can find an index I and j such that, look at f of I, the vertex which is assigned at f of I, look at the vertex which is assigned at f of j, they are same, because W. So, look, this is where it comes, like, so it is colorful, but it is it is an incorrect CPS, incorrect colorful potential solution means a vertex is repeated. Okay. So, I can find an index I comma j, vertices are same, that is it, and I is strictly less than j. Okay. 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 So, what are we going to do? Among such pairs, we are going to choose lexicographically first pair I comma j. I will tell you in a minute what I am, right. Among all this, so basically what it means is that, look at this example, V1, V2, V3, V4, right. Look, V3 is repeated here, V4 is repeated at here, V5. So, what are the indexes we are going to get? So, the indexes that repeat are 3, 7, 4, 6, and 5, 8, right. So, maybe if some other, like, if say for example, if 3 would have been occurring 3 times, then you would have been 1, like for all 3 pairs you will have. So, among all such indexes that repeat, okay, what is our lexicographically smallest? Is like, lexicographically smallest means that for the first coordinate you choose the smallest, and then you choose the smallest among the second coordinate. So, essentially what it means, that first index whose vertex repeats, okay, that is the first coordinate, and the second, the index on which this vertex occurs second time is what basically, not basically, is what lexicographically first object will be. What? Look at the first vertex which repeats. So, that is your first coordinate, like look that index the first, and look at the first time it repeats, like Look at the first time it repeats that that index corresponds, that I comma j corresponds to lexicographically first pair. Okay. Okay. So now I am going to give you a map from S incorrect to S incorrect. So what is S incorrect consist of? A W, a coloring function, and F function. So I am going to give you a map. So W remains the same, F remains the same, just the coloring will change. Okay. So let I comma j be the lexicographically first pair of W that repeats. So what is the new coloring function? Look, if so, what happens? So here it's a I and index j. Okay. So I I say, look, for all these indexes here and here, keep the same colors. But suppose I came at index, suppose x is I, then I assign this guy new color, which is the color of j. So this is like becomes color of j. And when I go to I, right? So if x equal to j, which means this, I assign the color. So basically I swap the color of vertices on index I and j. Right? That's it. That's all. So what does coloring function did? It looked at this pair and it just swapped the colors of these guys. Okay. Okay. First of all, notice that W col f is not equal to W col tilde f, because since coloring is an injective or colorful. This is where you, right? So, I mean, you have just swapped it. So coloring functions are not going to be same. But f and W are same because the walk is same. F assigns the same vertex. Okay, this is the first one. But now let's write down their monomials. Okay, let's write down their monomial. So what is the monomial of W col f? Is like T1 to k x f t and the color of t and the edges. Let's call this edge as z because edges in this walk are not going to change. So it's right z. But now let's from this let's remove I comma j this. Then what is this? X f of I call I, x of f of j call j. But notice what is x of f of I call I? It is same as okay, but what it has become in next, right? Now you have to replace this with x f of I call tilde I in the new one, and this with call tilde j. But what is this, right? This is this and this is this, right? So this is same as monomial W comma call tilde comma f. Okay. So what can we observe? We can observe that W call f is maps to W call tilde f, right? But let's ask ourselves, what is the phi of W call tilde comma f? Right? Notice that lexicographically pair will not change. Right? Lexicographically pair will not change. So again, if you apply phi to this, you will get back the call function. Right? Look at the assignment process. W remains the same, index ij remains the same. Then what will phi do? Coloring differs from colors only at ij, and that also flips the color of I and j. So what you are able to get is that phi W call tilde comma f is W call comma f. Right? So what does it implies? Now let's look at this. W call f is not equal to W call tilde f. So if you look at phi function, you apply it phi to twice, you will get, so right. So first I apply phi, I get call tilde, you again apply phi, you get back the same thing, right? So these kind of functions are also called, such phi is called fixed point free convolution. Okay. So such phi is called fixed point free convolution. Okay. Since the field f is of characteristic 2, monomial W call f and monomial W call tilde f will cancel out because they have the same monomial. So now what we have been able to achieve? We have been able to achieve the pairing function, right? That okay, look at this, if they have an incorrect C pairs, then we can pair them out, and over field of characteristic 2 they will cancel out each other. So what we have know, if P is not identically 0, then there is a K path. Okay. So let's look at that P, right? So right? So if P is not identically 0, then there is a K path, because we know that given any correct CPS corresponds to a path because of our first property, right? But because all the incorrect CPS will cancel out each other. Okay. Now let's look at P, right? So P is S in S call mon S, monomial S, and this monomial function. So I have just explicitly written down the monomial corresponding to this. Okay. Question. There are two things I would like to say. So look, we have been able to show to you that if P is not identically 0, then there is a K path, right? Okay. Okay. So let's look at this P. Okay. Question. Why do we exactly need A comma B, right? We had this A and we had this B. Why not only A? Just this edge variable, vertex variable. Why vertex color variable? Why edge variable? There is a reason for it. I'll show you. Okay. So look at this A, B, C, D, E. Okay. And so if let's write down the color 1, 2, 3, 5, 3, 5, 4. So you get this vertex. Okay. Now let's look at another path on the same vertex set A, C, E, D, B, and just change just take the same coloring, right? So 1, C was assigned 3, you assigned 3 here, E was assigned 4, you assigned 4, D was assigned 5, so on. Now if you write down these two monomial, they are same, right? Right? Two distinct paths get same monomial, right? Two distinct paths get same monomial, okay? Which implies that if I do a field of characteristic 2, they will cancel out. So what is happening is that, look at same set of vertices. There could be two different paths on them, first of all, right? There could be two different paths on them. Just the ordering of the vertices could change, because look at a click, you have n factorial ways of getting a Hamiltonian path, right? Now, if you just also fix the colors on these guys, like same vertex gets the same color, just at whichever occurrence, then these two guys will multiply and give you the same monomial. But since these two are distinct paths, edges are distinct and they will differ. Okay? Okay. So that's a reason why. Okay. So now if you add A, then they are YAB, YBC, YCD, YDA. Edges are different and now they are distinct, right? So you do not want correct CPC, correct colorful potential solution to cancel out each other, and this is why we have added this edge variable, because if two distinct paths, their edges are definitely distinct, right? So you can never cancel out them, right? So which implies that every correct CPS that is a path gets a unique monomial. So now what we have shown, that if P is not identically 0, then you know there is a K path in G, and if there is a K path in G, then P is not identically 0. Okay. So this is what we started so we have been able to obtain a polynomial. What is the property of this polynomial? That if P is not identically 0, then there is a K path in 0, and if there is a K path in G, then P is not identically 0. So P is not identically 0 if and only if there is a K path in G. So that's it. So now we have got our polynomial P. The question is, how do we evaluate P? We'll see this later. Okay. However, to evaluate, we are going to use Schwartz Zippel Lemma. So what is the degree of this polynomial? It's just 2k minus 1, right? Because look at any monomial, it consists of k variable, vertex variable, and k minus 1 edge variable. So 2k minus 1. Okay. So what are we going to do? Randomly assign elements from field F to variables such that probability of this is not equal to 0, is at least 1 minus t over F, given that P is not identical equal to 0. So this is what we are going to use. Okay. So we are going to choose field F of size more than say 10D. So the field F L will be like roughly log base 2 10D. Okay. So what is now, if G comma K is a no instance, then we get no with probability 1. So, if you do not have a path, then you do not have path. But if g comma k is a yes instance, then you know that this polynomial is not identically 0, right? And if it is not an identically 0, then if you do this random evaluation, then you will say yes with probability 9/10. Okay. So, that is it. So, now this is how we are going to do, like how do we evaluate p, we will come to this, but this is how we will do evaluate. Okay. We will apply Schwartz Zippel Lemma. We know that its degree is 2k minus 1. We choose a field f of size at least 10d, and we will do this. Okay. So far so good. Now, let us talk about evaluation of p. What is p? Remember, p is summation t in S call monomial of t. Okay, monomial of t. Okay. Okay. So, this is what our p was. So, now we are going to do something more. Now, what is S of L? It is a potential solution that uses only colors from L. Okay. Now, we are not talking about colorful potential solution. Okay. Okay. No. Okay. We are talking about potential solution. Okay. So, potential solution, what is the point of potential solution? Potential solution are walks. First of all, we are not talking about incorrect potential solution, colorful potential solution or correct colorful. No, we are just talking about potential solution. So, potential solution, if you recall, was nothing but walks. Let us just go back and good to okay, walk on k vertices that are colored. Okay, that is exactly what. So, okay, so this is a colorful, this is a potential solution, right? Look here, vertex are also repeated and colors are also repeated. Okay, okay. So, this is what potential solution, and we had refined that to talk about colorful potential solution and then good and bad. Okay, so just like so, we have gone back to just talking about potential solution, which is nothing but walk where vertices are colored. Okay. Now, potential solution may not be colorful. Okay. So, a potential solution may not use all the colors in L, right? Only thing we are saying that look at this, like what is the S of L? Those potential solution where the set of colors used is a subset of L. That is it. Okay. Okay. So, potential solution may not be colorful, a potential solution may not use all the colors in it. So, this is what S of L means. Okay. Okay, so what is S of L? W call comma f, W on k vertices, and call function is from 1 to k to L. So, what is P of L? Is by definition T in SL monomial T, right? And we know now how to write monomial corresponding to SL. Okay, so let us try to see what this P corresponds to. So, let us ask ourselves, I want to say that the P which we made is the P which we made with respect to S call is summation L subset of k. Remember, our definition of P was summation monomial T in S call, right? S colorful. Okay. So, I want to say this is nothing but summation L subset of k PL, and then this is just an extension of that. Let us see why. So, notice if T is in S call, then it is counted only once in left hand side for L equal to k, right? Because what is the property of S call, right? It is colorful potential solution, right? So, it means all the k colors are used. It could be, it may not be path, but on the, it could be a walk, but all the k colors are used. This is the definition of P which we came up with. Now, so if T is in S call, then it is only encountered for L equal to k. Only once in LHS for L equal to k. So, now let S all be all potential solution and T star be in S all minus S call. So, T star is W call F such that call of W is not, is a proper subset of 1 to k. We will show that T star occurs even number of times in left hand side, like T star occurs even number of times. So, when you sum them up, the monomial corresponding to T star is even and they will contribute 0. Okay. So, now look at, just ask yourself, look at, suppose the call of W is uses color Q. Now, look at any Q tilde which is a superset of Q, then T star is going to appear in S Q tilde. So, now you ask yourself, how many Q tilde are there? It is 2 to the power K minus cardinality of Q, which is 2 power A is greater than equal to 1, because this is a proper subset and hence this is even. So, this is very much similar to using inclusion exclusion, which we can establish this formula over okay, this is over a field f of characteristic. This is very important, otherwise we cannot say this, right. So, what we have been able to show that summation T in S call mon T is summation L subset of K PL, okay, PL, where P, right, over field of characteristic 2. Now, we will show how to evaluate PL, okay. So, rather than evaluating this, right, we will try to take this definition to evaluate P efficiently. So, now look at, I am going to tell you how to compute, how to evaluate one particular PL in polynomial time and polynomial space. Now, how many terms are there? So, the number of terms is like 2 power k. So, that will automatically imply O star 2 power k algorithm, that is 2 power k, poly n and poly space algorithm. Okay. Okay. So, now we have established this formula. All that remains to show is how to compute the evaluation of PL. This is a simple dynamic programming algorithm. So, let us just spend few minutes on that. So, evaluation of P is this. So, SL is potential solution that uses only colors from L. Okay. So, SL is this. So, we have reduced this to evaluating PL by definition T in S L mon do, and we will do dynamic programming to compute PL. Okay. So, you know that what is the dynamic? So, you know that these variables has been assigned numbers like xi's. Now, you want to evaluate P of L on these points. Okay. So, we are going to have MVL. So, we are going to keep a 2-dimensional array which will keep the evaluation of the polynomial mon s going over, where W is a walk on, but this is only going to keep an evaluation of a part of my polynomial. What is a part of my polynomial? W is a walk on L vertices, okay, that ends at a vertex V, and the first L vertices uses color from 1 to L. That's it. Okay. Okay. So what is MVL going to compute? It's going to compute evaluation the polynomial mon s going to W comma call f, where W is a walk on L vertices that ends at a vertex V and this. Okay. So, now what is MVL? So, we are going to write this. So, look, if I am trying to construct a path, like compute all walks of L vertices, okay, that ends in V, it means I must end in some U which is an in neighbor of V. Okay. Okay. So, summation U in neighbor of V. Okay. And after that, I have to take this edge UV. So, this is an edge U. This is how your polynomial is. And it is a summation over this, and summation also what? And also, this last vertex could get any of the color assigned. So, you also have to put in the summation I in L XVI. But what you have computed previously, you already have computed. So, I can write this is nothing but this is nothing but this into summation XVI I in L. Okay. Right. So, clearly this can be computed in polynomial time. You already have computed this. You just put up, like you put up the substitute all this mu you have summation, just put up all this substitution and you can compute this in polynomial time. Okay. So, this is a very simple evaluation. Okay. You can do this and you will be done. Okay. Now, the question is, so just one point I would like to make before we end this. Does this work for undirected graph? Answer is no. Why? Because look at u, v, w, x, 1, 2, 3, 4, x, w, like say x, w, just change it and change the color. These paths and their reverse will cancel out, right? But that's not a problem, because what you do, you fix a vertex v and you only look for paths starting at a vertex v, say u. So you fix one vertex and say, look, I'm only looking at a vertex which starts at u. Okay, then this proposition will not happen. Okay, so this is how you can make, with just this small fix, you can make this also work for undirected graph. Okay, that's all will be in this week, and that's it. Thank you very much.